So the final trend that we're going to talk about in the periodic table is electron affinity and electronegativity, which are related to each other. So electron affinity is the energy required to add one electron to an atom. If the electron affinity is negative, then we say that it is favorable to add an electron. And if the electron affinity is positive, we say that it is unfavorable to add an electron. In most cases, the amount of energy to add the first electron, or the electron affinity for the first electron, is usually negative because it's usually favorable. It's written like this: X plus electron gives us the anion. And the reason why that's typically favorable is that the nucleus in X is going to pull, and it's going to pull on one more electron. So this is usually a favorable process, especially for nonmetals. The second electron affinity, or the electron affinity for a second electron, is always positive, which means it is always unfavorable, because there's going to be a repulsion between the anion that you've already made and one more electron. They're both negatively charged. You've got your anion, you've got your electron that you're adding. These are both have a minus charge, so you have to overcome that repulsion, force them together. So that's always going to cost you energy. It's always going to be overall an unfavorable step. The trends in electron affinity are not nearly as regular as for size and for ionization energy. There's lots of exceptions. However, overall, electron affinity increases going across the periodic table, especially at the end. It really goes up. And it decreases going down a group, especially on the right side of the periodic table. And that's because we get farther away, the electrons get further away from the nucleus, so the pull is not as strong. Electronegativity is related to electron affinity, and it's a measure of how much a bonded atom pulls on shared electrons. So we've got this bonded pair, X and Y here, and the electrons that they are sharing are drawn in the middle with a little line. And if we say, so Y is pulling on the bond and X is also pulling on the bond. If Y pulls more strongly than X, we say that Y has a greater electronegativity than X. And this imbalance that happens when one is pulling more than the other is really going to be important when we get into bonding. So that's really why we talk about it here. So we can determine or look up the electronegativity of all the atoms on the periodic table and figure out what kind of bonds they're going to make. The trends in electronegativity are exactly the same as for electron affinity. They increase as you go from right to left across the periodic table, and they decrease as you go up to down in a group. So in the upper right hand corner, except for the noble gases, they don't bond, so they don't count, but leaving those out, the upper right hand corner is the highest electronegativity, and that is fluorine, and the lower left hand corner is francium, and that has the lowest electronegativity. So the trend sort of goes across the middle and on a slant. So some other periodic trends which can be important are metallic behavior and acid-base formation. So as we look at metals and nonmetals on the periodic table, metals, which are on the left, lose electrons more easily than nonmetals. That's really what makes them metals. So we say that elements are more metallic if they are on the left side of the periodic table. So metals are on the left, and the most metallic metals are farthest to the left on the periodic table. Acid-base behavior, this is just something that's interesting related to what happens when elements mix with oxygen. So remember that oxides are binary compounds, so they have two elements, and one of them is going to be oxygen. So it's going to be some element, other element, plus oxygen, and those are called oxides. So the trend is that as you go from left to right, so this starts at sodium, which is on the left side of the periodic table, then magnesium, then aluminum, phosphorus, sulfur, chlorine. Chlorine's on the right side of the periodic table. All of them are making oxides, so they're all bonded with oxygen. On the right side of the periodic table, they make acidic compounds. When you put them in water, they make acids. And on the left side of the periodic table, the oxides are basic when you put them into water. So there's definitely a trend, and it has to do with the elements pulling on electrons or giving up electrons, and the oxides being an anion, in this case, O minus 2. And here, the oxygen does not have a minus charge. So that's related to the acidity, and basicity of what happens to the oxides.